Now, the textbook then proceeds to give us an account for some existing particles that we have discovered. There are many, many particles. There's a big table for that. What we want to do is something a little bit different. Okay, we're not going to exactly trace back the historical origin when people found a lot of particles. Then they decide, gee, let's figure out what's behind those particles. Are there ways to classify those particles? We want to do it the other way around. We want to make a picture more clear by starting with the existing theory of the fundamental building blocks of nature and build these particles, even though this is historically it was the other way around. It turns out that out of the hundreds of particles that people discovered, people initially thought only neutrons, protons, and electrons, right? And everything can be built upon that. And it turns out there are many other particles, lambda, sigma, K, all these weird particles, and the numbers are still increasing. We're talking about hundreds of them. And there's so many particles that Enrico Fermi famously quipped, if I can remember the names of all these particles, I will be a botanist. Okay, so the point is not to remember all these particles, but to understand how we can build them up from simpler building blocks. According to today's theory, the so-called standard model, all matters, all particles can be classified into three types: leptons, quarks, and field particles. Let me explain to you. Leptons are believed to be truly fundamental particles. They have no internal structure whatsoever. The word lepton initially means light particles, because the first one and the most famous of all leptons is the electron. Indeed, it is very light compared with neutrons and protons. But that doesn't mean all leptons are light. In fact, the tau discovered in 1975 has twice the mass of a proton. It is not very light, but we still call them leptons because tauons and muons and electrons, they belong to the same general category. They don't have an internal structure, and we associate with each of them with what's called a lepton number, which we'll see in a minute. And there are three massive leptons: electrons, muons, and tauons. Muons have about 206 times the mass of the electron. This is a lot more massive. It's about 2 GeV. And there are three other leptons. These are three neutrinos. Neutrinos. Remember neutrinos? And each of these neutrinos is associated with each of these three leptons. So electrons are associated with electron neutrinos, muons with muon neutrinos, tau with tau neutrinos. When I associate, what I mean is that when you see an electron, you will see this produced at the same time. When you see muon, you get this produced at the same time, and so on. Okay, and remember, each of them has an antiparticle. Electron is accompanied by a positron. Okay, the original muon was discovered to be a negative particle, and there are also positive muons, which is the antiparticle of this muon. So, these are the 6 leptons, each with an antiparticle. Okay, they each have a spin 1/2. These are all fermions, each spin 1/2. They do not participate in strong interaction. That is the signature of leptons. They do not participate in strong interaction. They will participate in electromagnetic interaction if they're charged, which they are, and of course gravitational interaction. But they are excluded from the strong interaction. And when it comes to strong interaction, particles that participate in strong interaction are called hadrons. Hadrons. All hadrons participate in strong interactions. And all hadrons are made by these 6 quarks. There are 6 quarks. These are the fundamental building blocks of all hadrons. And hadrons are categorized into 2 subspecies, baryons and mesons. The difference is that baryons are made of 3 quarks, and mesons are made of 2 quarks. That's the difference. Okay, and baryons, each baryon has a baryon number which is defined as designated as +1. Antibaryons, the antiparticles, are given a baryon number of -1. Quarks, mesons on the other hand have no baryon number. Their baryon number is 0 because otherwise we call it, we wouldn't call them baryon numbers because these are not baryons. Okay, why do we define these baryon numbers, lepton numbers, and so on? Because it turns out we need to check these numbers to see if a reaction can proceed or not. They are separate conservation laws we have to follow. We'll see that in a minute. Okay, so That's the difference between mesons and quarks, and mesons and baryons. It's just how many quarks you have. All mesons are made of two baryons, which is a baryon and antibaryon pair. The baryon, actually, they're made of two quarks. I'm sorry, two quarks, which is a quark-anti-quark pair. The quark has a positive baryon number. The anti-quark has a negative baryon number, so they cancel out. So there is no baryon number. On the other hand, with baryons, we have three quarks. Each of these three quarks has a baryon number of 1/3. So 1/3 plus 1/3 plus 1/3, you get a baryon number of 1. If you're an anti-baryon, then you're made of three anti-quarks. Guess what's the baryon number of each anti-quark? Yes, it's negative 1/3. Okay, so you get negative 1/3 times 3, which is negative 1. That's the baryon number for any anti-baryons. We'll see examples later. So with these 6 quarks and these different schemes of combination, you can have hundreds of hadrons. We'll see a part of that in a table later. And the third type of distinct elementary particles are field particles. These are the particles that mediate these interactions. Photons are exchanged between electrons or other charged particles in electromagnetic interaction. It is a field particle for all electromagnetic interactions. And when it comes to weak interaction, there are 3 particles: W positive, W negative, and Z zero. They're all massive bosons that they facilitate weak interaction. Gluons are exchanged between quarks, which facilitate strong nuclear force, strong interaction. So these are the 3 distinct types. So 6 quarks, 6 leptons, and a few field particles. So here's a list of these 6 quarks and 6 leptons. Let's take a look at leptons first. Again, there are 3 leptons, okay? 3 leptons that are massive, and these 3 are just neutrinos. So with them, they don't have any rest mass. They're called massless particles. The electron was discovered first, positron discovered later. The negative muon was discovered first, and the negative tau was also discovered first, ahead of the positive tau, which is its antiparticle. You see how massive the tau is. Okay, even the muon is not that light. Electron is the lightest and the most famous of all leptons. And these 3 are charged, and neutrinos have no charge, and so on. The quarks, there are 6 quarks. There are 6 quarks. The 2 most widely used ones are U and D. By the way, these each has a name: up quark, down quark, strange quark for S, charmed quark, bottom quark, and top quark. These 2 are the most useful ones because they are the ones that will build neutrons and protons, the 2 most famous baryons. Okay, and you can see the mass of each of them is about 1/3 of the mass of the nucleon. So that makes sense because the 3 of them together will form, a nucleon with a mass of about 1,000 MeV. Okay, I have here some combinations how these quarks can combine to form the given baryons, but we'll see that in more details later. So let's not worry about that for now. Let's take a more detailed look at the properties of these 6 quarks in the next. So here we have a more detailed picture, a more detailed list of properties for these 6 quarks: up, down, strange, charmed, bottom, top. They all have 1/2 spin. Okay, again, they're all fermions. The charges are different. They all have fractions of charges: 2/3 E for up quark, negative 1/3 for down quark, and so on. And all these quarks have a baryon number of positive 1/3, and their antiparticles will have a baryon number of negative 1/3, and they also have negative charge, opposite charge if they're anti-quarks. Okay. Besides the common quantum numbers of charge and spin, there are some unfamiliar quantum numbers. Baryon number is only one of them. There are also strangeness, charmness, bottomness, and topness. Okay, these are just names that scientists gave for the quantum numbers because a top quark, for example, has its own distinct quantum nature, which is not present in any of these other quarks. So we assign a new quantum number to it we just call it topness. That's just a name for it. It doesn't really mean top or bottom, literally. Okay, the bottomness is only belongs to this quark called bottom quark. It's just another dimension in its quantum state. It's just another quantum number. So, each particle has a distinct collection of quantum numbers. This is those are just the new ones that we usually do not see in protons and neutrons, because proton and neutron only need U and D. That's it. And here the anti-quarks, we put a bar ahead of it, on top of it, and bond number reverses to negative 1/3, and the charge is reversed. You see that all the charges are reversed, and all the other quantum numbers are reversed. Okay, strangeness, charmness, bottomness, topness. So these anti-quarks are indeed very different from the corresponding quarks. All right, so how do these quarks combine to form the familiar baryons and mesons? Here are some examples how they do that. Baryons, some famous baryon in this table, and some famous mesons on that table. Again, baryons are made of 3 quarks. Okay, 3 quarks, each contributing a baryon number 1/3, so baryon number is positive 1 for all these baryons. Antibaryons, negative 1. The 2 most famous baryons are protons and neutrons. Protons are made of UUD. Neutrons are made of UDD. Let's see if it works. Okay, first of all, the spin. Each of these 3 quarks has a spin 1/2. So the combined spin can be 2/3 or 1/2, depending on whether they're all pointing in the same direction or pointing, 2 pointing in the same direction, 1 pointing in the opposite direction, which is clearly the case for protons and neutrons because they all have spin 1/2. So 2 of these point the same direction, 1 point opposite direction. And what about charges? Well, let's see here. UUD, that's for proton. U, let's go back to this table. U has a charge of positive 2/3. So 2U will give you 4/3e, right? But D has a charge of negative 1/3. You see, 4/3 minus 1/3, what's that? That's positive 1, okay? So positive 1. What about neutrons? Neutrons have a construction of UDD. U is positive 2/3, D is positive 1/3, but you have 2 of them, so it's 2/3 minus 2/3. That's 0. Indeed, that's true. Okay, and you can keep on going. You can see all these lambda, sigma, all these lesser known baryons. They have their own quark composition. So that's a good way of classifying these baryons. It turns out all these complicated differences underlying, there are only 6 fundamental pieces that we only need to use to build them. And we're going to worry about those things a little bit later. Okay, now, mesons. Mesons are made of 2 quarks, or more precisely, a quark and an anti-quark pair. Why is that important? Because all antiquarks carry a negative 1/3 baryon number, so that combined with their positive 1/3 from the quark, the total baryon number is 0. Okay, baryon number is 0, so they're not baryons. That baryon number is 0. The 3 most famous mesons are the pi mesons because they facilitate in a force between nucleons. Pi 0 is U bar U. U bar U. Now look at U bar U. U has, this is U right here. Spin 1/2, charge is negative, positive 2/3, but U bar will be negative 1/3, negative 2/3, so that cancel out. It's a charge neutral particle. Spin is 0, okay? Spin of the pi mesons all 0, and because you can have 1 up and 1 down, so the spin is 0. And it's also charge neutral because U bar and U carry opposite charge, so it's charge neutral. Now this is positive charged pi meson. It's made of D bar D. Does that work? Well, actually, that wouldn't work. D bar D would give you a charge neutral particle. The actual composition is D bar U. Let's see if that makes sense. Okay, D bar, that's the anti-quark for D, and D bar is right here. It's got a charge of positive 1/3 E. Okay, what about U? What about U? U has a charge of positive 2/3 E, so you combine them together, indeed get 1 E, which is correct. And the baryon number is 0 because this guy, D bar, being an anti-quark, has baryon number 1/3, negative 1/3 U is a quark, so positive 1/3. That's good. And pi bar, or pi negative, is the antiparticle of of pi positive, so all you have to do is take all the quarks and turn all the antiquarks to quarks. See how that works? So you just reverse the charge and everything else is the same. Okay? And here's another example of mesons. That's the Jape sign meson. And that's a combination of C of the charmed quark and charmed antiquark pair. All of these mesons, there are many more examples. All of these mesons are again combinations of a quark and an antiquark with 0 baryon number. I have here an example of the antiproton. It is made of 3 antiquarks. Instead of UUD, you have U bar, D bar. It's got a baryon number of -1. And also, you reverse all the charges on each quarks when they go to antiquarks, so it has a charge of -1 instead of +1. Now, I circle these things out because if you take a close look, you'll find that there is an issue here with the Pauli principle. All these baryons, all these quarks are spin 1/2 particles, okay? They're all fermions. Look, they're all fermions. Okay? Fermions must satisfy what? They must satisfy the Pauli principle, the exclusion principle. Here you have 3 U quarks. Now, if you want to have 2 U quarks and you say, okay, one is spin up, the other spin down, right? But you have 3 of them. It's impossible to distinguish with spins, and they're all the same type. You know, U, it's not U and U bar. So how does that not violate the Pauli principle? We have a problem here, don't we? Same thing with DDD and SSS. Well, it turns out that, first of all, you don't want to violate the Pauli principle, and secondly, these things are real, okay? You can have actually 3 U quarks, because this guy does exist. So does this guy, so does this guy. So that's weird. So what's the way out? Well, the way out is that the Pauli principle says you must have something different, right? So they already have everything else the same, everything known that's the same. You know, they have spins and they have, you know, charges, whatever. So the only thing that's different is a new quantum number. That means these 3 U's are not exactly the same. Okay? They have something different, a new quantum number, or flavor, we should say. Just a term. It's actually a quantum number that tells them apart. And that new quantum number is called color charge. It doesn't mean these things are colored, okay? It's just, you know, it's just a easy way for us to illustrate that. So basically we're saying that these quarks, each has something different which distinguishes them from one another, and this new quantity is called color charges. Why do we call it color and what do we call it charge? Color is for one thing is for illustration, and secondly, there are 3 different flavors of color charge. Unlike electrical charges, which only comes in 2 flavors, we can call them positive, negative. Here we cannot call them positive because there are 3 different varieties. So we call them 3 colors, blue, red, and green. It just those colors are just a code name. It doesn't really mean they're literally green, red, or blue. But so that's why we call it color, because there's 3 of them, not 2. And they call it charges because they are similar to electrical charges in the sense that with electrical charges, the 2 particles can interact electrically with Coulomb force, and with color charges, these particles can interact through strong interaction. Okay, so it is in this sense we say they're called charges. And just like the electrical charges, unlike charges attract each other, like charges repel each other. Here you have 3 different flavors. They're all different. Okay? So this blue one and this green one, they will attract each other because they're not the same. They're different. But they're not opposite, right? Opposite means U bar, okay? If you had an opposite charge, so both are both are green, both are blue, but one is U bar, and they will attract each other even more strongly. These things are part of what's called quantum chromodynamics, QCD, not QED. Quantum chromodynamics is the theory of how quarks interact with each other to form hadrons. And in quantum chromodynamics, we can study the force between different quarks, and they exchange a particle, and that particle is called a gluon. A gluon, okay. So gluons are the field particles that facilitate strong interaction. And what about the pi meson then? Well, the pi meson is not a gluon, is it? It is in fact itself, made of two quarks. It does mediate the strong interaction between two nucleons, but these two nucleons are not two bare charges, not two bare charges like what you see one here, one there. You have one nucleon here, such as P, another nucleon there, such as N. When they get close enough, about 1 Fermi, each of them is charged neutron. Okay, when we say charged, I mean color charged neutron, because they have, each has one blue, one green, and one red, so it's charged neutral, charged neutral. So when they get close together, why do they still attract each other? Do they exchange gluons? No, they don't. But why do they still attract each other? This is pretty much like how a positive and negative electrical charges attract each other. Well, I mean, a charged neutral molecule, see, you got positive, negative here, and negative, positive here. You see, each of them is charged neutral, but when you bring close enough together, they can still get an attraction. Why? Because they can, have a positive side here, negative side. It's like a dipole-dipole force. That dipole force, of course, is weaker than the original positive negative force, right? Using this analogy, in this case, the original force are between the quarks and the exchange gluon. That's a very, very strong force. But when they get close together, there is a residual force between the strong force and the strong force there. That residual force, even though it's residual, it is still strong enough to bind these two particles together. That is the nuclear force that binds the neutrons and protons together. Just like the molecular force that holds these two atoms together, even though each atom is charged neutral. Okay, so, and they do that by exchanging a pion. So they do that by exchanging a pion. So pion is not a field particle, not a true field particle of the strong interaction. That will be the role of the gluons. But when the two pions get close together, they can in fact exchange a pion. So that's how they interact with each other. Let's see a Feynman diagram associated with that. So here's the Feynman diagram depicting the action between the proton and the neutron when they get close together. According to the original Yukawa idea, the neutron would emit a negatively charged pi meson, turn itself into a positively charged proton, and the proton will absorb that negative pi meson, turn itself into a neutron. There's nothing wrong with that, except we can get a better, a more clear picture by looking at the underlying action of the protons, which make up the neutron and protons. Here we have a DDU, which is a combination with that form a neutron. Here you have a DUU, which is the quark constituents of a proton. And this is what happens when they get close together. The proton and the neutron when they get close together. At this point, the D quark emits a pair of U and U bar. This is just like a photon can disintegrate into an electron or a positron. When it's energetic enough, it can actually form an electron and a proton. And if you have enough energy, you can actually create a U bar pair. And this U bar goes this way. The U that's created goes that way, and D, this original D, also goes this way. Okay, so at this point, this D splits into a U bar pair plus its original D, and so D and U bar goes this way, and this U goes that way. So this D has turned into a U. So now you have a UUD, just like UUD. So the proton is now turned into a neutron. I'm sorry, neutron is turned into a proton. And what is U bar times D? That is a pion, a negative charged pion. Okay, and negative charged pion, and is absorbed by this U. So this U gets together with U bar, and it just turns into energy. Okay, it's annihilation into energy, and then what's left is just a D. So this U has turned into a D. So this proton, which is DUU, is now turned into a neutron, which is DDU. So that's how it goes. Basically, it's the creation and annihilation of a UU bar pair from here to there, which caused the difference. So this is a more detailed, a more clear picture of what's really going on in the Yukawa's pion model. And this UU bar pair is created by an energetic gluon, just like an energetic gamma ray photon can produce an E positive and E negative pair. It's the same basic idea. So now we can take a look at some examples of of the hundreds of particles that we have discovered. As you know, some are truly fundamental particles, some are just particles made of more fundamental blocks. Leptons and hadrons. Hadrons are made of mesons and baryons. Okay, we have all the 6 leptons because there are only 6, so they're all here. Okay, they're all here. And the hadrons, they're just mesons and baryons. There are just hundreds of them. So we only have some famous examples: pions, kaons, and eta particles. These are 2 quarks, quark and antiquark pair. They're mesons. Baryons, the 2 most famous example: protons and neutrons, plus some lesser known ones: lambda, sigma, delta, and so on. This table goes on and on and on. You can see here, most of them not very stable. Electrons are certainly stable. Okay, protons are stable, neutrons are stable. Because their stability, they are the most widely seen ones. They have they dominate most of the masses in the universe. Okay, of course, neutrinos are also stable, but being neutrinos, they don't have any, they hardly have any mass, so therefore they don't really matter that much when it comes to massive particles. And all these other guys, you see, all these other guys are very unstable. They decay in a very small fraction of a second, so we can capture them by means of highly accurate, highly sophisticated, high energy equipment. But in the real life, we don't see them because they're not stable at all. Okay, and you also notice that the massive particles, the hadrons and baryons, they're all made of quarks, and quarks are fermions. Quarks are fermions. And over here, you have some particles that are not quite very light, such as, muons and tau and so on. But these are all fermions, okay? All leptons are fermions. So what does that tell us? It tells us pretty much all the masses in the universe are made of fermions, whether these fermions are quarks or whether fermions are leptons. But these fermions exchange interaction with each other. They can repel, they can attract each other by exchanging field particles. All field particles are bosons. Isn't that interesting?